So, as Mark said, the project itself is divided into 4 different themes. I'm talking about the first of those themes on devices, semiconductor devices. There'll be subsequent speakers on the other 3 themes following on from this. So I'm going to talk about the work that's been going on in the devices area. And as you can see, this is a piece of work that involves 4 universities. This is the new Warwick branding, by the way, if you've never seen that before. I don't know why we did that, but we've got rid of the old one and we've made it that. There's Bristol, Newcastle and Cambridge. Notice Cambridge don't keep changing their branding every 5 minutes. But Warwick does. It's obviously important for them. Right, so I don't expect you to read all of this, but it's what we said we'd do. It's what we said we'd do when we started. So we want to make a significant impact to the state of the art in the semiconductor technology area. And of course, that's a wide area. So we're not aiming to work in all the different areas. So we've picked a number of key areas. In particular, we're doing work on power IC technology in silicon. We're doing work on IGBT structures, superjunction IGBT structures, which I'll talk about in a bit, in silicon as well. And we're also working on wide bandgap devices, silicon carbide and gallium nitride, and their reliability. So that's what we said we'd do. And what I'll try and explain to you in the next 20 minutes, or however long I've got, is what we actually have done. So within this particular piece of work, there are 4 themes, or work packages. So the devices theme has 4 work packages. The first one, I'll just go through them all, is on power device design and fabrication. So in this particular theme, we're looking at advanced superjunction silicon devices, manufacture design of silicon carbide devices, and also producing compact models for those devices. The second theme, or second work package 2, is on interfaces and materials. So in any semiconductor device, there's lots of different interfaces between different materials, between silicon and silicon dioxide, between different semiconductors, different insulators, and this really is looking at those properties. In particular, we're looking at improving the quality of MOS interfaces for silicon carbide devices. Big issue. We're looking at methods to characterize the interface. And final part of this work is looking at the growth of high quality, thick epitaxial layers of silicon carbide. Thick being the operative word there for high voltage devices. So we're looking at layers bigger than 30 microns. The third work package is on reliability. So this is really looking at some of the underpinning physics and trying to understand what are the key issues that cause these new materials to be unreliable. Especially gallium nitride has a lot of problems with defects and how they change the device characteristics with time. So it's looking at building up a set of predictive models and also measurement techniques for characterizing that degradation in the devices themselves. It's not about the packaging degradation, it's about what's going on inside the semiconductor. And finally, the last work package is on integrated circuits. So here we're looking at, obviously, this is the biggest market segment in terms of where power semiconductors go into. It's enormous compared with the high voltage areas, but we're looking here at producing high voltage, and by high voltage here we mean 700 volts. High voltage IGBTs and MOSFETs, that integrate into a CMOS process so that you can build converters almost on a chip. So getting up to 700 volts is very challenging. And the challenging part is making the on-state resistance of these things as low as possible. So we're looking at techniques for improving the performance of these devices. So that's the 4 themes. That's how it's split up. And now I'm going to go through what's been going on at each of the universities. I thought it was better to do it that way than to go through those 4 themes in detail. So we're going to look at what Cambridge have been doing first, etc. So Cambridge, they've been mainly working on the first of those work packages and the 4th. So looking at super junction silicon IGBTs and integrated circuits. So the first one, the work package 1 on super junction IGBTs, are using, these are quite advanced structures actually. They're very sophisticated. Cambridge don't actually manufacture these, they design them and get them manufactured elsewhere at a foundry, but they're devices that they've designed and tested and produce and show some very promising results. So they're looking at quite low voltage breakdown IGBTs here, 1.2 kV. Recently, the results from this work have been published at ISPSD, which was in Hong Kong a couple of months ago. So the work there progressing very nicely. And here's the structure. As you know, if you're familiar with power IGBTs, then you'll recognize this as a very advanced form of IGBT. It uses trenches. A lot of devices are planar. These are most devices are moving towards trenches. But the engineering about how you make this top surface as effective as possible is very detailed. So this is a trench structure with an N+ injector here. So in this device, there's an oxide down the side of these trenches, which forms the sort of MOS structure. You get a channel down the side of the trench, and then this injector, so electrons would flow from the top through those inversion layers and enter this injection layer, and then be injected down here. So this oxide on the side of the trench here is what's actually doing the switching. This bottom part of the device is responsible for the voltage blocking capabilities of that structure. So what's often a problem is how you make this injection across the surface as uniform as possible. If it's only being injected from one point at the edge of the end of the channel here, then that will cause the resistance to be higher than it need be. So by spreading it out using this injector, gives you a much lower on-state resistance, causes the injection to be from both sides, very high injection from the top and the bottom. So it gives you the lowest on resistance. Now, the superjunction part of it is enabled by these P-rings here at the bottom of the trenches. Normally these trenches would have a P implant at the bottom anyway, but these have been extended and made bigger so that you can see you've got a sort of superjunction structure here. You've got an N-type region here and then these P-rings partially penetrating the depth of the drift region. And so these act as charge compensation parts of the structure. They make what's called a resurfed structure, reduced surface field as they be in a lateral device. And that allows you to increase the doping in this drift region as well. So this whole structure becomes a very effective and one of the most advanced forms of IGBT, certainly in the engineering of the top part of the surface that you can get. This is an SEM or TEM picture of one of those structures, actually an SEM it says there. But you can see there that you've got double trenches here rather than a single trench there. P-rings at the bottom, and there's the N+ injector there. And you can see that these feature sizes are submicron features. These trenches are very, very small indeed. And here's some of the results from those structures. First of all, in terms of the on-state resistance, VDS on, the on-state voltage drop, you can see that different types of technology here are tested. FS means field stop. This is the enhanced field stop, and this is the field stop with the P-ring. And you can see as you go up in generations of technology, then you reduce the on-state voltage drop. You're down here to 2.5 volts. And it's fairly temperature insensitive as well. If you look at the switching performance of these devices, on the left there, you can see that, again, there's a comparison between the fields, this generation of devices and the one with the P-ring. You can see that you get, the closer to this corner you get, the better the performance of the device. You can see there's a dramatic increase in the switching performance of about 20%, which is very significant for these type of devices. So that piece of work has been going on, and it's producing real devices now, and they are being looked at, are being exploited commercially. So work package 4 that Cambridge are also working on is on these 700 volt, 700 1 kV bulk silicon lateral IGBTs and MOSFETs. They've been, again, fabricated at a foundry externally and characterized. Just said that. The bare dies have been tested at different temperatures and different switching speeds. All the measurements are pulse tested. Some devices have started to have some reliability measurements done on them, and those and similar to that previous slide, the trade-off between the V-on and the turn-off energy are being compared. Right. So here's the chip, one of the chip layouts of this particular batch, MPW. I don't know what MPW stands for. They've pointed out these resistors. They're really to identify where you are on the wafer. These resistors have all got different values, and by probing those, you know where you are on the chip. So they're nothing to do with the power devices themselves. It's just to locate them. And you've got two sets of devices here, MOSFETs at the top and various sized IGBTs at the bottom here. And you can see they're lateral because of this cellular structure. So all the contacts are on the top of the wafer. The current enters and leaves on the top, and the gate structure is on the top as well. There's the characteristics of the MOSFETs. And there's the breakdown characteristics, achieving greater than 1,000 volts, which was the designed value. And that's a photograph of some of the lateral IGBTs. And some measured characteristics of the IGBTs as well. Again, these were going up to, these were exceeding the 700 volt design capability. So Cambridge are currently exploiting that technology as well. So move on to Warwick next. I'm not quite sure, this isn't in alphabetical order. I have to say thank you to a number of people who are working on this particular theme, especially Vishal and David Martin, who are here. These two are PhD students who aren't here, I don't think. Certainly Yegi isn't. But Vishal is our man who looks after the epitaxial growth system, and David is our device processing expert. We had the unfortunate situation that we did have another RA on this project, but he left at Christmas to go and work for Infineon in Germany, as happens. So here's some of the work that's been going on in this work package. Obviously, we want to grow thick epitaxial layers. Typically, to get to 3,000 volts, you need 30 microns here, and to get to 10,000 volts, you need approximately 100 microns of epitaxy there. And the problem is, when you grow those very thick layers, it's very, you don't just grow it on the wafer itself. Here's a wafer. You grow it all over the equipment, the chamber that's being used to grow it in. So it's very expensive because you have to clean out the chamber very frequently when you grow these thick layers. And it's also difficult to grow them quickly, and it's difficult to grow them with good quality. So what we've been focusing on is trying to grow these layers, thick layers quickly, and we can grow 100 microns in about an hour or two, which is very fast indeed, and the quality is excellent. We've bought an epi reactor for this. A special piece of equipment was we bought through linkage with this project, and it's the only one in the UK. So this, for silicon carbide, it's the only one in the UK that can be used to grow this material. So this is a picture of one of the wafers that we've grown. This had 3 kV, so 30 micron layer on it. You can see it's transparent, which is different to silicon. And this is an AFM picture of the surface. So in the surface roughness is quite acceptable. And the quality of the wafer is very difficult to compare qualities of wafer. So we tried to compare it with other suppliers. Now, really shouldn't have put the name of the supplier on here, but we have. And you can see that the purple one is our measurement of the wafer we grew, the epi layer we grew, and the blue one is from another company. And basically, the narrower this peak is, the better the quality of the material is. So we think we're doing a good job compared with commercial suppliers out there. And it's very difficult to get commercial suppliers who give you 100 microns of epi as well. This was probably one of the only ones you can easily go to and get those thick epi layers. We've also done some mercury probe measurements on those wafers to look at the sort of variation of the thickness across the of the wafer and the doping. And here you can see that we've compared again our wafers with a company we bought the material from, and it's pretty good. There's our one in the middle there. The doping could be a bit lower, but it's quite acceptable for a first 1 or 2 runs. The thickness of the wafer is pretty much identical to what the suppliers of the equipment can grow as well. So we found that the thickness is less than 2% across the wafer, which is what you can buy commercially. And we also found that there were small amounts of contaminants, but they were pretty much below the detectable limits. And so we demonstrated that the growth process was very high purity. So at that point, we've now got a system where we know we can grow high quality epitaxial layers. And some of the physical characterization that we've done on those layers is shown here. Using transmission electron microscopy, what you have to do with TEM is to cut out very thin films through the structure that you want to look at, so that you can pass electron beams through it and look at the cross section. So we've developed a novel technique for making very thin sections using standard lithography to start with. It improves the speed at which you can do that dramatically. There's some pictures of some of the looking through some of the epi layers that we've grown, and of course we've got AFM to look at the surface profile as well. That's quite challenging. We've also been making structures using some of the epi layers that we've grown to try and evaluate the quality of those epi layers in real devices. So we made some pin diodes. We made this type of structure. There's one there. So they're a mesostructure with all the doping here. All these different layers are grown using epitaxy. These bits here around the edges are implanted. When we did quite a bit of trial and error here, the first few samples that we had this sort of bumpy IV characteristic, but we found out that this passivation here wasn't quite good enough around the edge, and if you improve the passivation, you end up with very nice quality characteristics like that. We've also done some work on some lateral MOSFETs on these structures, on the EPIs that we've grown, and you can see that we've got some mobilities which are about 20. Typically, this is using some post-oxidation anneal process. Typically, when you grow these oxide layers on silicon carbide without doing some processing, you get mobilities of down here. So this is like 4 or 5 times better. We've actually improved this quite considerably now. We've got up to 40 now, so it's on a different scale. We've also been doing quite a bit on characterization of implants. So these are simulated implant profiles, and we've also taken those through this simulation program and compared it with SIMS measurements on the actual devices and found them to be pretty much identical. Okay, so I'll move on now to the work that's been going on at Newcastle University. Again, it's a team of people. I don't know if anybody's here there's people here from Newcastle University, definitely. I don't think Nick's here, pretty busy man, because he's the Pro Vice Chancellor, and Anthony O'Neill, and then 2 research fellows there. I don't know if they're here. Should be. Maybe they're late. So, what have they been doing? Again, they've been looking at trying to improve this oxide interface. But in the previous example that I showed you, there was actually thermally grown oxide. Here, what they're trying to do is to use different materials for the gate oxide. So it's not MOS, it's metal insulator semiconductor. And they've been trying to use alumina on top of a very thin layer of silicon dioxide. So you have an extremely thin, just a few nanometers of normal silicon dioxide, and on top of that you put an ALD deposited dielectric, and the literature seems to point at, this is taken from the literature, that you get extremely high mobilities. Remember, we had about 20. The peak mobility here is over 300. We've not seen that yet, but that's what is promised using this technique. So we're supplying some epi layers to Newcastle, and they're building these structures on top. They have some unique processing capabilities to deposit this material. It's not to scale that. Another piece of work that they've been looking at is trying to implement some superjunction structures in silicon carbide. Obviously, you get the same benefits if you can implement superjunction structures in silicon carbide as you would in silicon. And so people have started to look at this, and this is one of the first practical demonstrations of that. I mean, what you're trying to do is, this is the way a normal superjunction device is built up, with making N, P, N, P, NP pillars. This is difficult to do in silicon carbide, because the way they do this in silicon is with either lots of implantations to build up the P pillars, or they etch out a hole here and regrow epitaxy inside. Neither of those is really suitable for silicon carbide. So we're trying to look at what happens if we can build this structure using epitaxy. And there's some initial simulation results. Shows that you can get pretty much close or exceed the one-dimensional limit of silicon carbide by using these superjunction structures. And here's some more. So that piece of work is just started to make some devices. They've not actually got any results on that yet, but they will have in the next few months. This shows some work that they have been doing some measurements on, which is trying to look at this interface. So there's the silicon dioxide, looking at this interface between silicon dioxide and silicon carbide, and looking at the defects or the material that's here. You always get some sort of graded layer there, which is neither silicon dioxide or silicon carbide, but a mixture of the two. And they've been probing that interface to look at what's there, because obviously we don't want that there. And so if we can remove it, brilliant. This shows some more simulations of the superjunction devices and how important it is to get the doping in the P columns and the N columns as close to each other as physically possible. Otherwise, the blocking voltage falls off very quickly. This is where it's balanced at in the middle, so the charge in both those pillars is the same. If it falls one way, you can see that the blocking voltage falls off very quickly, and if you get it the other way, it falls off very, very quickly. And that's part of the challenge in making these devices. Okay, so this is the final university of Bristol. So they've been working on reliability and probing some of the gallium nitride devices. This is a general slide. Just shows you where we are with these different materials. I think most people have probably seen that, but if you haven't, then you can see that silicon superjunction devices are here. That's the one-dimensional limit. Superjunction devices exceed that. So the further you get over here, the better. This is the silicon carbide limit, and gallium nitride may be even better still, although that's not been reached yet. So in terms of reliability, this is a typical bathtub curve. You get early failures, which always happen, and you try and filter those out when you're manufacturing, and you never let them get out of the factory. Then the device will wear out with time. So it's these wear out mechanisms in the device that Bristol have been looking at. And eventually those wear out mechanisms lead to the devices failing. And of course, you'd like this to be as far over in time as possible. But it's understanding those mechanisms and how they accelerate which is important. So this shows a picture of a gallium nitride HEMT. There's the structure. It's an SEM from looking at it from the top. You can see that you've got the source, drain, contacts there, and these are the gate fingers here. The gates are very, very thin. They're very thin stripes that go between the source and the drain, and of course you apply voltage here and it allows a current to flow from source to drain. That's an AFM image looking at along this edge. Now, what they found is that with time, as you stress this device, then the leakage current through the gate increases. It increases exponentially. And that's due to defects forming. And you can see these little red dots here. They are pointing out defects on these gate fingers as they grow with time. And this is a zoom in of that. You can see these little pits that occur along the fingers. And they multiply with time. They get more of them. And they emit light, so they're quite easy to see. They emit blue light. And this shows a picture of there's that curve, the gate leakage again, increasing with time. And here's the electroluminescence, the light that comes out of that gate structure. And you can see it pretty much mirrors that. So you can just look at the light that comes out around the gate finger and try and gives you a good indication of how well you've made the structure. If there's no light, then you've made an effective structure. This is a count of the number of defects, those little red blobs, increasing with time as well. You can see they all increase. They're all linked to each other. These defects are being produced, and they're producing light, and they're as well producing gate leakage current. So what happens is these defects get to a certain size, and then they saturate. They don't get any bigger, but you get more and more of them developing along the gate interface with time. So the distance between these pits gets closer as time goes by. And various mechanisms for that have been identified, and these have been published in the literature. They tend to occur right here at the corner of the gate. So there's the edge of the gate there. You can see these things grow, and they tend to grow out in fingers along away from the gate, and eventually the leakage and the light occurs at the end of these fingers as they grow with time, and that's been published recently. So I think that's probably the last slide, and it covers some of the work, or all of the work, that's been going on in the devices theme over the last year or so.